Okay, we're going to continue on here, chapter 14 still there. So last time really we got into sort of titrations and titration curves, and we're going to talk about obviously a few other types of titrations here in this chapter. But last time we kind of covered the strong acid, strong base titration. This is typically what the titration curve looks like here. The sort of S sort of shape that happens. Reminder that what we're doing here is in the burette, we have the base. So in this example, sodium hydroxide. And down in the flask or the beaker or whatever you may have, we have our acid sample is hydrochloric acid. So this is again a titration of a strong acid, strong base. We're adding again the base to the acid here. And when we look at the titration curve, or really any titration curve that we'll be talking about here, there really is sort of four parts to the titration curve. The very first part is really kind of like before you even start the titration. So as we talked about in this type of titration, before you really start the titration, the only thing that you have in the beaker really is your strong acid. So if we need to figure out which of our sort of starting solution, because it's a strong acid, that pretty much gives us the ability to go right into the pH equation, because we really should have the H plus concentration from the strong acid. So we can just kind of go right into it. Don't have to worry about really anything like that. We obviously haven't added any base or anything like that, so there's no worry about volumes or molarity changing. So we could just get the molarity there of our H plus, which again, in most cases will be the same as the strong acid, and you can get the pH. Now, from sort of the first drop there to the equivalence point is technically kind of the second region of a titration curve. And in this part of the titration curve, we actually are adding base. And because we're adding base, we will get a chemical reaction that's going to occur. And in this case, it will be hydrochloric acid plus some sodium hydroxide. It's going to be a normal sort of double displacement reaction where we will get some water and some sodium chloride in this case, as these guys basically switch partners in that sense. We do need to do an ice table here. So you do need to do an ice table. And this ice table should be done in moles. Again, here we are adding volume from the burette to the beaker. So you do your kind of normal sort of ice table, if you will. In this case, though, because we are doing it in moles and we are before the equivalence point, the moles of the sodium hydroxide should be less than the moles of the acid that we're starting with. And that means that really the change part should be the moles of the sodium hydroxide, as that would be in this example here, the limiting reagents. Once you do that, what you'll see is you'll have none of the sodium hydroxide left. You'll have some moles of your sodium chloride in this example. You'll have some moles of your hydrochloric acid. As we talked about, it's really good practice after you do the first ice table in moles that you do convert it back into molarity at that point. What we would be using, as we talked about, is really the total volume. So that would be the volume of the acid you started with, and really the volume of the base that you added to it at that point, obviously converted to liters so that we do end up with molarity. What you'll see at that point is we do not have, again, as we talked about, we don't really have a buffer, but we do have a strong acid left over. And really the purpose of this ice table is to figure out how the concentration of the strong acid has changed as you're kind of dropping your sodium hydroxide as you get close to the equivalence point. When we get near the equivalence point, we do see sort of a couple things happening that we talked about, and really that is the third part of a titration curve, which is the equivalence point. We do typically see this kind of vertical rise to the equivalence point followed by, after the equivalence point, another sort of vertical rise. And as we talked about, that is really, what happens when you do a titration, for example, and you just add one drop of it, solution, and the indicator goes to a really dark color. Although you may have added a very small volume, you might have been able to change the pH a lot, and that's going to be reflected in your indicator color, as it will change to perhaps a darker color. As we talked about, there's really no kind of difference in a sense of the volume of those 3 points. But there is a big difference in terms of the pH at those 3 points. And because indicators do work on a pH range, that's why we can sometimes see a pretty big jump in color of our indicator, even though, you added just like a drop or so as well. But when we do reach the equivalence point, remember that's sort of the definition of an equivalence point in acid-base titration is the point where the moles of the acid will equal the moles of the base. So when we reach the equivalence point here in a strong acid, strong base titration, these guys should pretty much be gone. You'll have the exact same number of moles. You will be left with just a salt at this point. And as we talked about, that salt does come from a strong acid, strong base, which means it should be a neutral salt. So in this type of titration, we do expect the pH at the equivalence point to be 7 or neutral, because ideally the only thing you should have left at this point is a salt that will not go through hydrolysis, and you'll have water basically. So we should expect it to sort of be neutral. The fourth part of the titration curve is really after you go past the equivalence point, and you hopefully eventually stop. Again, we see that kind of big jump in pH along the way. This does require you to do an ice table. Also should be done in moles. What you'll see when you do the ice table in moles is there's sort of a switch that happens in the sense of, in this example here, for taking a look at this one, if we go past the equivalence point, we actually will have more base than acid. So the acid actually becomes like the limiting reagent, and it gets used up first, and that's actually going to be your change part. What you'll be left with at the end there is actually just a strong base, and also the neutral salt is not going to do anything. So here, really the purpose of this ice table on the back end of the titration curve here, past the equivalence point, is to figure out really what the concentration of your strong base is at this point, because you're just adding base basically to your titration. And once you have your base, that will allow you to go POH and then to the pH at that point, and you can get your pH of that solution. So those are really the 4 sort of really important points on a titration curve. Again, before you begin, before the equivalence point, at the equivalence point, and then after the equivalence point. Remember that it's always good to kind of know where you are in the titration, and you can really figure that out if you're not sure by the moles of what you're adding to what you started with. So if they're equal, you're at the equivalence point. If the moles of what you're adding is less than what you started with, then you're before. And if the moles of what you're adding is more than what you started with in terms of the acid, then you are past the equivalence point. So that's sometimes helpful as you do these type of calculations to kind of have an idea as to where you are sort of in the titration curve. Any questions on that part there? All right, so why don't we try one like this from this one here? Let's do say, what is the pH after 21.5 milliliters of 0.1 molar sodium hydroxide is added to 25 milliliters of 0.1 molar HCl. All right, so give it a go. Okay, let's take a look. So obviously we're doing a titration here. So again, we're adding the sodium hydroxide to the HCl. So that means we are going to get a reaction. That also means we do need to do an ice table, and we do need some moles. So we'll start with the moles here of our sodium hydroxide. We do need to convert our volume into liters. So that's a 0.0215 liters. We're going to times it by the molarity there of our sodium hydroxide. which is 0.1 moles per liter. And that will get us there 0.0215 times 0.1. Give us a 0.00215 moles of sodium hydroxide. We do need to do the same thing here for our HCl, converting our volume into liters, times it by its molarity as well. Gonna get us there 0.0025 moles of HCl. So now we can do our ice table here. We're going to take our HCl, which is what we're starting with. We're going to take our sodium hydroxide, which is what we're adding. And again, that's going to give us some water and a little sodium chloride action there. We're going to go initially here with our moles of HCl, which is 0.0025. We're also going to do our moles of sodium hydroxide, 0.00215, and we're going to go 0 here. So the first question is, are we before, are we at, are we past the equivalence point? We are before the equivalence point. We know that from looking at our ice table. If you're not sure, the moles of what we're starting with is more than the moles of what we're adding, which means we are before the equivalence point. Remember, if we're at the equivalence point, they're equal. So obviously, if what we're adding is less than that, then we haven't got there yet, right? And if it's more than that, then we are past it. So we are before the equivalence point here. Because of that, we know that we really have kind of not enough sodium hydroxide there. It's sort of the limiting reagent. So that again is going to be the change. And as we talked about, I think a number of times last time, logic tells us that we should always take the smaller number. So again, that is definitely the one that we want to take so we don't get any negative type numbers. That means when we reach equilibrium here, we'll have 0.0025 minus 0.00215, giving us 0.00035 moles, 0 and 0.00215 moles over here. Any questions on the ice table here so far? We do want our total volume. So in this case, our total volume, we started with 25 milliliters. We added 21.5 milliliters. So that looks like a 46.5 milliliters is our total volume. We're going to convert that into liters and convert this back into molarity here. So we'll divide by 0.0465 liters. I'll spit that out maybe. That was 0.465 liters. There we go. And 0.0465 going to give us a 0.007527 molar. And over here on the other side, 0.0465. That's going to give us there a 0.04624 molar. So if you're not sure what's going on, we do have these two things here, which they are related to each other. Are they a buffer? They're not. So again, we're not going to use the Henderson-Hasselbalch equation. Even though we have two numbers, we do want to analyze what we got going on. We do have our neutral salt, so we're not going to really be concerned really about that guy. That means really, as we should expect here before the equivalence point, we should expect to really only have the strong acid left over. And that again is, as I talked about, really the purpose of this table was to figure out really how the concentration of your strong acid has basically changed. And now that we know how it's changed, we can go right into our pH equation because that's HCl, which means that will be our H plus concentration. So the pH in this case minus the log there, 0.007527. Gonna do a little minus the log. Gonna give us a pH of 2.12 at this point in the titration. Let's see how we did. This was this titration I think we were looking at. So we're at 21.5, which is right there between those two numbers. 2.12, that fits. That's nice. Didn't screw up too much. Any questions on that there? Yeah.
It's like these like excess reaction problems.
What's that? Is it?
Excess reaction
It is really a titration. A titration curve in this case is really limiting reagent, excess reagent type of thing, especially in this particular type of titration. It is. You just got to figure out where you're at, and then you know really which one's limiting and which one's the excess. Yeah. Other questions? So in general, obviously, before you get to the equivalence point, your whatever you're adding is the limiting. Once you go past the equivalence point, whatever you're adding becomes like the excess. Yeah. If you just think about logically of what you're doing, if you've done the titration, which you obviously have, that's like when you hit the pink part, right? You're technically kind of done with the reaction. So if you just keep adding sodium hydroxide, you're basically just keep adding base, right? And so you got plenty of excess base, for example, past the equivalence point. Question on a strong acid, strong base titration. Once again, you need to be able to calculate the pH anywhere along the curve or 500 points along the curve that I give you for the exam. This can be one exam question, titration curve, 400 points. Give the pH all the way across there. Let's all drop together. All right, let's talk about the next. Let's talk about the next type of titration curve we're going to talk about. Maybe if it's there, there it is. So we're going to talk about titration of a weak acid in this case with a strong base. So this is a different type of titration curve. It is set up sort of the same way. In this case, we are adding the base from the burette, and we have our weak acid down in the beaker or flask or whatever you're adding it to. So again, here we're really adding base to our acid. So for example, if we use our acetic acid, which is a weak acid, and we add some sodium hydroxide to it from a burette, once again, we'll get a double displacement reaction, which will make a little sodium acetate and some water in this case, right? Again, double displacement, basically. All right, so we do see this titration curve, and it is similar looking in terms of that sort of S shape there, as we saw with the strong acid, strong base. And just like the previous titration curve, we really do focus in on sort of those same four spots. So again, here, our first spot would be before we begin the titration. The second spot is once you start adding, but before the equivalence point. And the third spot there is at the equivalence point. And just like the previous one, after you go past the equivalence point until you kind of stop, that would be after the equivalence point. So once again, these are the four kind of important areas of this titration curve. We do see a similar sort of pattern. We're starting in an acidic pH and we're ending in a basic pH, which makes sense since we're adding base to our acid. So we would expect it to sort of come up. So let's talk about what's happening here at each of these steps, sort of like what we did on the previous one. So we'll start with the first step there, which is before we start the titration. So before we start adding base. So once again, in this case, before we start adding base, we pretty much have acetic acid in our beaker. And because acetic acid is a weak acid, it will break apart into H plus and a little bit of acetate floating around. Right. So if I wanted the pH of a weak acid, what do I do? We could get the pH by an ice table, yeah. And it's really a Ka type problem, right? Because it's a weak acid, it will have a Ka. So here to get the pH, we cannot go, by the way, directly into the pH equation because it is a weak acid. It does require you to, again, do an ice table, as I mentioned there. This ice table you can do with molarity since you have not added any volume or anything like that. And this would be a normal sort of Ka type ice table with some zeros, some X's. Kind of our initial minus X, X, and X. Like normal, right? We would go into the Ka expression. You would solve for x, whatever that means, by making an assumption, doing the quadratic, whatever you want to do there. When you do solve for x, as we can see from our ice table here, x will equal the H plus concentration, and it's at that point you can then go into your pH equation. So as we can see here with this type of titration curve, it is a little bit different than the previous one. And that's because, again, here we are using a weak acid versus a strong acid. So because we're not using a strong acid, we do have to do the ice table because it's weak to get our H plus concentration and then go into the pH equation. Any questions on that there? So once again, it is something that we've done previously, and that is how you should approach this. This is also why you might see a slightly higher starting point there than, say, in the strong acid one, again, because it's a weak acid, and as we know, with a weak acid, it's not going to give out as much H plus. It's going to be free versus a strong acid, so you might start at a little bit higher of a pH. Any questions on before we start titration? All right, then let's talk about the second part, which is we are going to actually start the titration here. So we're going to actually start the titration. And we'll be before the equivalence point. So when we do the titration here and we start it, we will get a reaction. So we will need a reaction that's going to occur. So we'll have a little acetic acid. We'll have our sodium hydroxide. Once again, that's going to create our sodium acetate in this case, and our water. Because we are adding, we do want to make sure that we do this table like the other one in moles. So we do want to make sure that we do this guy in moles. This is, again, what we're starting with. And this is what we are adding. So just like last time, I'm just going to make up some whole numbers, nice kind of round numbers here. So I'm going to say we started with 4 moles of our acetic acid. So because we are before the equivalence point here, we should know again that the moles of our sodium hydroxide should be less than, equal to, or greater than 4. Should be less than, right? Because we're out now as equivalence point. So again, just making up the number for future reference there, that is 2, and that's going to be 0. Because we are before the equivalence point, as we've been talking about, that means whatever we are adding is going to be the limiting reagent here. And that means that will also be the change. So -2, -2, and a +2 over here. That means when we do reach equilibrium, we'll have 2 moles of this guy, 0, and 2 moles of that guy. Any question here on the ice table? Just like normal, our good practice here, we will take our total volume in liters and convert these guys back into molarity. Once again, as I mentioned before, the ice table really gives you a lot of information, can sort of help you figure out perhaps, what's going on. As we could clearly see there, we do have less moles than what we're starting with, so we know we're before the equivalence point. We could also look at this and see what we got left over after the end of this part of the reaction. So we have acetic acid and sodium acetate. Are they related to each other? They are. They're related to each other as what? What is that? That is a buffer, yeah? That is a weak acid and the salt of its conjugate base. So by doing this reaction before the equivalence point, we just made a buffer pretty much, yeah, which is like part 3 calculation of, what's going on in lab coming up this week. So by reacting a weak acid with a strong base, we do end up with a buffer. And by the way, the buffer is what is left over. It is not what we started with. So what's left over here at the end is the actual buffer. Now, because it is a buffer, we could actually do 2 things. Probably the best move is go into our Henderson-Hasselbalch, which is what that equation is really for. So we can go into our Henderson-Hasselbalch here to get the pH. Alternative to that, you could do a second ice table. So if you want to do a second ice table instead of the Henderson-Hasselbalch, you can. Remember, again, as we talked about a number of times, you want to make sure if you do the second ice table instead of the Henderson-Hasselbalch that you got an initial concentration on both sides, in this case for acetic acid and the acetate. Otherwise, you're not really doing a buffer problem. So you want to be really careful when you do that. So as we can see here, this is much different than the previous titration here. We end up with a buffer problem. And by the way, you will end up with a buffer problem all the way through any type of titration like this before the pretty much make a buffer. That is why when we look at the titration curve here, you know, we have a little bit of rise in pH. And as we get closer to the equivalence point, we're essentially going to break our buffer. And again, that is why we're going to see that jump in pH to the equivalence point. And we'll also see sort of that jump after the pH as well. So we'll get this kind of big jump once you kind of get through that buffer part that you made, and we'll get to the equivalence point. Any questions on before the equivalence point? So let's talk about what happens at the equivalence point. So we made a buffer before the equivalence point. Now we're going to get to the equivalence point and see what happens. Once again, here we will have our reaction. A little sodium acetate and some water here. Once again, we're starting with this guy. We are adding this guy. So maybe using our made up number 4 moles, we know that we are now at the equivalence point. So we should again have an equal number of moles of what we're adding, because that's pretty much the definition of the equivalence point. And we will have 0 here. The good news at this point is you can't really pick the wrong number, hopefully, because there's only one number to pick. In this case, it is 4, and that will be our change. That means we will end up with 0, 0, and 4 moles of this guy, a little total volume to convert back into molarity at this point. Any questions on this so far? We can again look at our ice table and see what we have left. This is sodium acetate. That is a salt, yes. Do I need to worry about this salt? Should the pH here be 7? No is the right answer, by the way. It should not be 7, and I should worry about this salt. So this salt is sodium acetate, which means it's going to break apart into 2 things, a sodium ion and an acetate ion in this case. All right, we'll start with the sodium. Sodium is what type of salt? Acid, basic, neutral. It is neutral, right? Because it kind of comes from sodium hydroxide. How about acetate? It comes from this guy right here, which is a weak acid, which means this would be the conjugate base, and will it go through hydrolysis? It will, right? So anything that comes from a weak acid or a weak base will go through hydrolysis, which means that is what's going to happen in this case. We're actually going to have this guy react with the water that's there, and you will need a second ice table that is a hydrolysis ice table, where the acetate, which is going to act as a base in this case because it comes from a weak acid, will accept the H+. It will then make acetic acid, which it always makes where it comes from, and it will make OH-. That means the pH right now at the equivalence point should be acidic, basic, or neutral. Should be basic, right? Because we just created hydroxide. We will do an ice table here, and our equilibrium concentration of our salt will become our starting concentration here, right? This ice table will be done in zeros and X's. This is going to go into my K expression. By the way, what K is it? A, B, C, D, F, G. Now I know my ABCs. It should be a B because that's a KOH right there. That's a OH minus. So it should be a KB. So this is a situation where you will probably have the Ka value given to you. So this is one of those situations where you use your Kw equals Ka times Kb to flip it around. So you'll have to kind of do that guy as well. So you'll probably need to do a little Kw equals Ka Kb to get to the Kb value. Once you have that, you could solve for X. The important thing to also remember, though, when you do solve for X in this case, it is the hydroxide concentration, which means that you got to do a little POH first and then to a pH. My, oh my. Also, why it's quite important to make sure that you do convert back to molarity after the first ice table. You don't want to go into this second one with mole. So you want to make sure it's in molarity at that point. Any questions on that? So obviously much different than the previous titration where you're just left with a neutral salt where the pH should be 7. Here you will always, in this type of titration, at the equivalence point, you will always have a salt left over, and you will always have a salt that will go through hydrolysis because it comes from a weak acid. And by the way, it will always produce hydroxide. So you should always expect the equivalence point in this type of titration to be basic. This is also why you use something like phenolphthalein, which works from like 8.3 to 10 in terms of pH, because this is the titration you did in Chem 50, basically. Acetic acid and some sodium hydroxide as one of them probably that you did. And that pH at the equivalence point should be basic, and that's what the phenolphthalein works in, the basic range. So that's oftentimes why you use that a lot. So at this point, at the equivalence point, you do need 2 ice tables. First ice table is really just to figure out the concentration of your salt. The second ice table is a hydrolysis ice table, basically. Any questions on that there? All right, let us then talk about the fourth part here in the titration, which is after the equivalence point, and see what happens here. And when we get to after the equivalence point here, we're still going to have our reaction happening. Again, we're starting with this guy. We are adding this guy. So initially here, we'll start with our made up 4 moles. So now that we are past the equivalence point, we know that whatever we are adding should be more moles than what we started with. So again, I'll just make up 6 moles. Sounds good. At this point, we do get that switch that sort of occurs. The acetic acid here is going to be our limiting reagent. It's a smaller number. So we will use the 4 as our change in this case. At equilibrium, we'll have none of those guys. We'll have 2 moles of this guy, 4 moles of this guy. Like normal here, we'll convert back to molarity using the total volume that obviously has been converted into liters. Upon looking at our ice table here, we could see really what is left over. We have a little sodium acetate. We have some sodium hydroxide. Is that a buffer? That is not a buffer. So again, just because you have 2 things, don't throw it into the Henderson-Osbach equation. So we got a couple of things here. We definitely have the salt that we just saw that will basically be a base, right, and go through hydrolysis. We also have sodium hydroxide, which is a strong base. So really at this point in the titration, we kind of have 2 bases left over. Out of the 2, between sodium hydroxide and sodium acetate, which one is the stronger base? Yeah, the NaOH is a strong base, which means all it has to do is be added to it from your burette. And as soon as it goes into the solution, it's going to break apart into OH minus and basically just provide OH minus. The sodium acetate's got to go find some water, right? Do a little bit of a reaction and produce some hydroxide. So out of the two, it really is going to be our strong base here that's going to be the major contributor of hydroxide. So typically what we do in this point of the titration curve is we actually ignore the contribution of the salt because again, really all he has to do is drop that sodium hydroxide into here and you're just going to create a bunch of hydroxide really quickly. So because of that, we'll look at just the strong base, which means that should be the hydroxide concentration, or you could get the hydroxide concentration from it, which means you could get to the POH and then to the pH in this case. So this part is very similar to the previous titration, except that we still have that salt is going through hydrolysis, but again, out of the two, really that sodium hydroxide that you keep adding past the equivalence point is definitely going to be your major contributor. So the purpose of this size table really is to figure out again what the concentration of your strong base is at this point, so that you can get the OH minus and then the POH. Any questions on this type of titration here? So we have the same 4 parts as we do from the previous titration, but very different in terms of what you should be calculating. We basically have a Ka problem at the beginning, a weak acid problem. We have buffer situation happening there before the equivalence point. We got a hydrolysis situation at the equivalence point, and we have a strong base past the equivalence point. So once again, knowing where you are in the titration curve is really helpful, because if you know where you are before you even do the calculation, you should really have a good idea as to what type of calculation you're supposed to be doing. So sometimes it's good to know where you're going right before you get there. And you have sort of directions of how to do the calculation rather than just diving in and just trying to work it out as you're doing it. So again, I would recommend taking a moment or two and try to figure out where you are. And like I said, that should click in this type of titration as, oh, I should be doing like a buffer situation. I should be doing, hydrolysis, or I should be doing like a Ka type situation or a strong base. So that's oftentimes very helpful. All right, so let's try one here. Let's do what is the the pH after 23.5 milliliters of 0.1 molar sodium hydroxide is added to 25 milliliters of 0.1 molar acetic acid. Ka for acetic acid, everybody's favorite, 1.8 times 10 to the minus 5. All right, so take it and work it out. I'll do it as well. All right, let's take a look, see how we're doing. So obviously we're doing our titration we've been looking at. So we're adding our sodium hydroxide to our acetic acid. So obviously we know we're in the titration, so we do need moles. So we're just gonna start with that. So our moles of sodium hydroxide here. Again, converting our volume into liters will give us 0.0235 liters. Times it by our molarity here, or 0.1 moles per liter for our sodium hydroxide. That's going to get us there 0.0023 moles of sodium hydroxide. We'll do the same thing here for our HCl. 0.025 liters times our 0.1 moles per liter. Going to give us our same sort of starting amount there that we had previously, 0.0025 moles here of HCl. Doing our reaction, a little HCl. That's not HCl, that is acetic acid. It's kind of not like HCl, really. Okay, well, the HCl seems smaller to write. All right, let's try the right acid there, which is acetic acid. There we go. All right, so using our acetic acid would be much better. There we go. Plus our sodium hydroxide here. Going to give us some sodium acetate, just like previously, and our H2O here. Using our initial moles here of our acetic acid, 0.0025. Our moles of our sodium hydroxide there. Oh, moles. And 0 here. So again, we're starting with this guy. We are adding our sodium hydroxide. Am I before, am I at, or am I after the equivalence point? I am before. Again, what I'm adding is less moles than what I started with, so I'm actually before the equivalence point. That means that what I'm adding should be the change here. So because we have less of this guy, minus 0.0023. Minus 0.0023 and plus 0.0023. Gonna give us at equilibrium here 0. 0.002 moles, 0 this guy, and 0.0023 moles of this guy. Question on the ice table here. We want our total volume. So at this point, we started with 25 milliliters. We added 23.5 milliliters. So that looks like a 48.5 milliliters, if I'm not mistaken. So we're going to divide everybody here by 0.0485 liters, right? 0.0485 liters. All right, so 0.0002 divided by 0.0485 going to give us 0.00412 molar. Over here, 0.0023 divided by 0.0485. Going to get us there 0.0474 molar, I believe. So at this point, we can look and see really what we got going on here. We have acetic acid left over. We have a little sodium acetate left over. Those two guys, again, are related to each other. They are a buffer, and that's exactly what we should expect to happen here because we are before the equivalence point. That means that we can go into the Henderson-Hasselbalch equation if you like. You can also use the right numbers here as well, would be even better. I can see it's going to be one of those days here today on that thing. We shouldn't change, hopefully, too much. We'll see. So that's going to give us a 0.0015 and 2.5 here. And that would be divided by 0.0485. That would give us actually all right, let's try this again here. 309. Banner day here. I said 2.35 divided by 0.0485. 484 looks like. Not too bad off. All right, let's try that there. That might be a little better, hopefully. All right, so now that we got the right numbers there, sorry about that. We should be able to go into our pH is equal to pKa plus the log of the base over the acid. Our pKa value in this case will equal minus the log of 1.8 times 10 to the minus 5. That's going to be 4.74. That'll give us 4.74 plus the log of the base part, which should be this guy here at 0.0484 divided by our acid, which is 0.00309, I hope. All right. Let's hope so. 0.00309, a little log action of it, plus a 4.74. I'm going to go with a 593, hopefully. I hope. Any questions on that there? Sorry about that. I think I lost the 5 there on the top one there. I'm afraid to look, but see how bad I did there. We're at 23.5, so 5.9. That's between them at least, so that's good. All right. Looks good. Any questions on this type of titration here? All right, so this is the second type of titration curve that we're looking at. We're now going to look at the last type of titration that we will do. And again, we'll look at the different parts of that. So let's take a look at this guy here. So the last type of titration curve that we're going to actually do is actually a titration of a strong acid with a weak base. So this is a little different in terms of what's happening here is we actually have the strong acid up in the burette. So we're going to be adding the acid to the weak base. So in this case, so a little bit different. Instead of adding the base to the acid here, we're going to add the acid to the base. This is also why the curve looks upside down, because when we start, we have a base, which should be a basic pH, and we're adding acid, which means we're decreasing, right, in terms of the pH as we come down here. So sort of starting high and ending low here in this type of titration curve. There is still, not surprisingly, the same 4 spots. The before you begin, the before the equivalence point, there is at the equivalence point, and then there is obviously past the equivalence point there. And this type of titration. So let's just start with the first part, which is, and in this case, we'll do something like we're going to do HCl and ammonia. Ammonia being a weak base, HCl being a strong acid. In this case, we will get ammonium chloride, which you can either put together like so, or if you want to keep them separate, you will get NH4 plus and Cl minus. So whichever kind of way you want to do that, you can. So obviously here, before we start the titration, which is the first part, so before we add any strong acid, really the only thing that we have in our beaker is a weak base. So because it is a weak base, you would do really a KB problem. So kind of similar to the last titration where we had a weak acid to start with, you do kind of like a Ka type problem. Here you're going to really do a KB problem, a weak base problem. So if we used ammonia here, you would set up an ice table where it's going to accept the H plus and make NH4 plus and OH minus in this case. This, again, you could do in molarity as you haven't added any volume. So you could just use the initial molarity of the weak base. These would be zeros, minus X's, plus X's. Initial minus X, X, and X. This, because it is a base, would go into our KB. We would solve for X. And in this case, as we can see from our table, X would equal the hydroxide concentration. So you would need to do an ice table in molarity with X's to get the concentration of X, and that would be the hydroxide concentration. That, remember, is still the hydroxide concentration, which means that you can get the POH first, subtract 14, and get yourself to the pH. So it's very similar to the previous titration, except instead of doing a weak acid problem, you have to do a weak base problem here at the very beginning of the titration. questions on that there? All right, so now we're going to talk about what happens here in the second region. We are seeing the pH starting to drop once again because we are adding acid. So it's going to bring the pH down in this case. So once we are before the equivalence point, we will once again get a reaction between our hydrochloric acid in this case and our ammonia. And once again, as I mentioned before, you could either kind of keep them together or you could break them apart to different ions. So for these calculations here, I'm going to break it apart and I'll kind of tell you why in just a second. But I'm going to keep them apart. Initially here, we are adding our HCl. We are starting actually with the weak base. So I'm going to do my 4 moles here as we've been using previously. And just like previously, since we are before the equivalence point, the moles of the HCl should be less. So I'll make up 2 and 0. Change here is going to be -2, +2, and +2 here. And that means at equilibrium, none of this, 2 moles of this guy, 2 moles of this guy. By the way, I ignored the Cl minus because, yeah, it's neutral salt, so it's really not going to do much. So if you do break it apart, you can kind of ignore it. If you keep it together with NH4Cl, it's okay as well. At the end here, we're going to, like normal here, convert back to molarity by dividing by the total volume. Any questions here on the ice table? Yeah. Why are we adding? We shouldn't be. We should be subtracting, except that I'm having a banner day and writing the wrong things there. So thank you. That should be subtraction. Yeah. There you go. Thank you. So yeah, it should be definitely -2, -2, +2 over here. Other questions? All right, so we can look at our ice table. We got this guy left over. I got this guy left over. Are these things related to each other? Yes, they are a weak base and its conjugate acid, also known as a buffer. So very similar to what happened in the previous titration will happen again in this type of titration. You will create a buffer as you're going through this. This is taking a weak base and reacting it with a strong acid will actually generate a buffer in this part of the titration curve. It's called in vitro. It happens in the beaker as you're doing it. You create a buffer as you're going through it. It's also known as method 2, as I was talking about earlier in our lab on Thursday. So this is going to create a buffer, which means we can go into our Henderson-Hasselbalch equation here. Or once again, you do have an option to do a second ice table if you would like, instead of the Henderson-Hasselbalch. You will need to sort of think about a couple of things, and those couple of things are, in this situation, you would probably have just the Kb value given to you. So you might want to convert it to a Ka and then into the pKa. You also could convert the Kb into a pKb, subtract 14 to get to the pKa. So remember, though, that you do need the pKa here. You most likely, in this case, will have the Kb for that guy. So you got to do a little bit of calculations there to get the right value in there. Also remember base over acid. Alternative to that, if you don't want to do all that, you could do the POH version of the Henderson-Hasselbalch equation that we talked about and use the pKb and do the acid over base and then subtract 14. Your option as well. So it just depends sort of how you want to do it. Any questions on that there? So it is kind of similar, this one, to the previous titration. We do kind of get similar things happening here, but it is sort of opposite. Instead of, going kind of from acidic to basic here, we're going from basic to acidic. So let's talk about what does happen here at the equivalence point. We again do also see, as that buffer breaks, a drop in this case of the pH to the equivalence point and a further drop after the equivalence point as we get near it and past it. So once we do get to the equivalence point here, we have our equation. reaction. All right, so once again here, we're going to start with our 4 moles. And since we are at the equivalence point, we know we should have equal number of moles. So we should have the same number of moles. Change here going to be -4, -4, and +4 here. That means at equilibrium, 0, 0, 4 moles of this guy. I once again just going to kind of ignore the chloride here as it's a neutral salt. We're going to convert this back into molarity using our total volume. The only thing we got left is a salt, right? We basically have ammonium chloride left over. We've already crossed out the chloride part because we know it's neutral. So that means, should I worry about the ammonium part of it? Will the ammonium part go through hydrolysis? The ammonium comes from this guy, right? And this guy is a weak base, which means this will be a conjugate acid that will go through hydrolysis, right? Because it comes from a weak base. So that, much like the previous titration, is exactly what's going to happen here. We're going to get a secondary reaction that's going to occur with our salt that will go through hydrolysis. It will act as a acid, which means it's going to donate the H plus over. And that's going to give me NH3, which is where it comes from, and H3O plus in this case. That means without doing the calculation, my pH at the equivalence point in this type of titration should be acidic, basic, or neutral. Should be acidic. By the way, when I do this ice table that I'm going to do, I need a K what? I do need a Ka. Once again, here you will have the Kb given to you. So you need to do that sort of crossover. Just like in the previous one, whatever our equilibrium concentration of this salt is will become our initial concentration here. This guy will be done with zeros and x's. And as we just talked about, that is going to be a Ka situation. So once again, probably a Kw, Ka times Kb you're going to need to use to reverse that. In this case, though, we would then solve for x once we have the proper K value. And in this case, that actually does equal the H plus concentration, which means you go right into your pH equation at that point. So just like the sort of previous titration, in this titration, it does require 2 ice tables. The first ice table is simply to figure out what is the concentration of your salt. The second ice table is basically a hydrolysis ice table where you solve for X and you will hit acidic. So this is why in this type of titration, we would expect the equivalence point to be acidic. Also why if you want to use something like phenolphthalein as your indicator, it would be a crappy choice because it's going to change in the basic part, right? So if you chose phenolphthalein, you've already seen it go actually from pink to colorless, and it's going to be colorless for the rest of your titration, which is not going to do you much good at that point, right? So again, this is why knowing what type of titration you're doing is also really good when you're trying to pick maybe something like a good indicator to use in a titration, because they're not all the same. You just don't use the same one for every type of titration. Any questions on that there? That brings us to the fourth part of the titration, which is it didn't stop you there, the equivalence point. You're just going to keep adding. So let us do this one here. We're going to go past the equivalence point. So once again, we have our reaction. Adding, we are starting. All right, so we've got our 4 moles. As we talked about in the previous 2 titrations, we are past the equivalence point, so we should have more than what we started with. So 6 moles will work. Here we get the switch that it's actually the base here is going to be our limiting reagent. So the change should be the smaller number, which is 4 in my example. Gives me 2 moles, 0, and 4 moles. Once again, we're going to convert into molarity by dividing by the total volume. We have this guy left over, and we have this guy left over. You hopefully should recognize that that is not a buffer, right? They're not really even related to each other. So we do again have the salt that will go through hydrolysis and act as an acid. We also have HCl, which is a strong acid. So much like what we did in the previous titration, although the NH4 plus will go through hydrolysis, it is nowhere near as strong of an acid as HCl, which is a strong acid. Once again, HCl just needs to go in for a swim. It's going to create a lot of H plus really quickly. So it's going to be the major contributor here to the pH. So at this point in the titration, past the equivalence point, we ignore the salt's contribution. We go with a strong acid, which means that that would be the H plus concentration. And then we could go into our pH at that point. So here, much like the other one, you're just actually dumping a bunch of acid into your beaker. Any questions on that there? So this titration is very similar to the previous one, except that obviously, like I said, it's got to go from basic to acidic, but really it's the same 4 parts. Before you have a KB type problem. Before the equivalence point, you have a buffer problem. At the equivalence point, you have a hydrolysis problem. And past the equivalence point, you have really a strong acid problem. Question on that there. So let's just try one here to finish up here. Let's do what is the pH after you add 27 milliliters of 0.1 molar HCl to 25 milliliters of 0.1 molar ammonia? The KB for ammonia is, we'll go with 1.8 times 10 to the minus 5. All right, give it a go. I'll do it as well. Hopefully I won't screw up as bad as I did previously. All right. So again, then let's take a look at it here. So obviously we're going to need some moles since we've titrated. So we'll go with the moles of the HCl. I'm going to convert our volume into liters here. Going to times it by our molarity. And 0.0027 moles of HCl. We'll do it for our NH3, 0.025 liters times our 0.1 moles per liter. 0.0025 moles. We will have our reaction, our HCl, and our ammonia, making our ammonium chloride basically. I am again just going to kind of keep them separate. Initially here, HCl, we got 0.0027 for NH3 0.0025 and 0. Again, we're starting with this guy. We're adding. Am I before, at, or after the equivalence point? I am after because I have more moles, so I am after the equivalence point in this case. That means that the change is actually going to be our NH3 since it's a smaller number, minus 0.0025, minus 0.0025, and a plus 0.0025. That means here 0.0027 minus 0.0025, going to give us 0.00020, I think, moles. And we'll have 0 here, 0.00250 in this case. We are going to convert back into molarity by our total volume, which is our 27 and our 25 milliliters there. We obviously, again, want to make sure that we convert our 52 milliliters into liters, 0.052 liters, 0.052 liters. So we'll go 0.002 divided by 0.052, going to give us 0.003846. Over here, 0.0025 divided by 0.052, 0.04808. At this point, if we look, we know we're not going to worry about this guy. We have basically these two guys left over. As we talked about, and as we know from the start of this ice table, we're past the equivalence point, which means we're not going to concern ourselves with the salts hydrolysis. That means that we really just have this strong acid left over. And that's going to be the major contributor of H plus, which means that should be our H plus. And that means we could go right into our pH, really. And that will get us there 0.003846 or 241 pH, which is acidic, which is good because we're past the equivalence point. And we'll see how bad I did there. That puts us, should be between these two numbers, 2.4. Looks like it's between those two numbers, so that's not bad either. Any questions on that there? Yeah. Would we add a weak base to a strong acid? You could really do any combination there, but these are the three common ones that we come across in most cases. Yeah. Other questions? All right, a couple of things here. We'll stop here for now.